I've been working with Heidi Newberg and also with collaborators from Georgia State University who made the data set that we're going to be using. And we're going to be talking about two massive radial mergers in local solar neighborhood dwarf stars. Perfect, so the movie made it in. So this is what a radial merger looks like. And so it goes quickly, but there's going to be a dwarf galaxy that comes straight into the center of Milky Way-like galaxy. And then it's going to pass through and make these shells as it comes through. And then over time, these shells are going to mix as different energy levels of the radial merger pass back and forth between sides of the galaxy. And then shells become less noticeable as the mixing process continues. And then finally, at something like, say, 8 gigayears, which you can see in the top right corner, there is going to be basically no shell structure left. It's going to be essentially completely phase mixed. If you looked for shells, you weren't going to find any. And so there's a phase mixing argument to be made, which is there substructure in the inner halo? Do we see that? And if so, then how do we explain that substructure? And that can tell us a lot about the time of the accretion of these things. So you got a little bit of this from Jesse's talk, but just to jog your memory again, there's the Gaia sausage Enceladus merger event, which is currently thought to be basically all of the inner halo. And it was this massive merger with a sizable dwarf galaxy that crashed into the Milky Way at early times and supposedly puffed up what was the Milky Way's protodisk and made this thin disk. And so based on the ages of thick disk stars, you say that this had to be about 8 or more gigayears ago. It was discovered independently by a few different groups, but it's characterized by this big sausage velocity structure, which I've circled in red here, which you saw in Jesse's cuts. And so this is like the canonical Gaia sausage, because apparently to some people that looks like a sausage and a meatball. And so we are going to be talking about another merger event that is possibly in the halo that we call the Virgo radial merger. And this was actually discovered in Virgo overdensity stars, which is the overdensity that Jesse was talking about in the north. So if you take stars in that overdensity and actually run their orbits, and then you can fit an N-body to that orbit, then you get something that looks like this in the local solar neighborhood. So instead of this big smooth sausage structure, you get this kind of what we call dumbbells or double-lobed thing. And so it is puffed out on either side at about the same radial velocity in positive and negative, and then there's fewer stars in the middle. But the weird thing was that we were able to do this with just a 2 billion year N-body simulation. And in fact, if you did it for too long, if you did it for more than 5, the substructure went away in velocity, and you didn't really get anything except just a double Gaussian in the middle. And so it's weird that we were able to get this sausage with something so young, with Virgo overdensity stars, but so it raises the question of whether the Virgo radial merge and the Gaia sausage are the same thing. Are they different? What's going on here? So when we have this type of tension, we go back to the data. And so Buckyoung Kim at Georgia State University constructed a catalog of Gaia EDR3 dwarf stars within 2 kiloparsecs of the sun. And you see clearly that there's this thick disk in red, which we've cut out some of it by a proper motion cut. And then there's this Gaia sausage in the bottom that you see. So we've got the sausage structure in the local solar data. And for this data set, we only have proper motions, but that's okay because proper motions are going to be tangential to your line of sight, and you get the 2 directions. And so if you just look at the poles up and down, those 2 tangential velocities are going to be oriented in your radial velocity and your rotational velocity. So you can get your sausage plot back just from the proper motions if you're looking in the right way. And then you get a metallicity for each star by making isochrones, and then you plot those isochrones on a color magnitude diagram, and then you take where each dwarf star lies on that CMD, and you extrapolate its metallicity based on that grid. And so we now have 5D space, so no radial velocities, but we also have metallicities for these. And so we wanted to see what happens if you start to break these up in metallicity, because there should be a clear metallicity signature of the Gaia sausage. So we do that. So each of these panels is a split in FV on H, which you see there up above each panel. And what you get is really interesting is that if you ignore the thick disk in that red circle, and you just look at those radial stars in that gray band, you actually get that there's kind of like almost a smooth kind of sausage looking thing in the lower metallicities. And then when you get up to minus 2.2 on the top right, you get these clear velocity lobes. You get that dumbbell structure that kind of pops out at you. And then when you go back up to about -1 in Fe on H, it goes away again. And so what's happening here, because in Jesse's plot, they had a peak at Fe on H at -1, but we don't see that. We see that this sausage structure is actually more prominent at about the -2.2 to -1.4. And so that's kind of weird. And so we went back to the theory where we ran a whole bunch of radial merger simulations. And so we said, all right, we maybe aren't quite sure what a radial merger event actually looks like if you're just looking at velocities in the solar neighborhood. So each one of these is varying in certain parameters of radial mergers. We vary things like progenitor mass. We vary things like inclination, the final apogalactic distance, which is essentially energy of the collision. And then we cut it all to the solar region. And then we plotted it in velocity. So it's kind of like that sausage plot on the bottom panel. And then there's a histogram of that up above. And turns out inclination doesn't matter too much. But when you vary the progenitor mass, you either get, as you go very high, you get this kind of just single Gaussian thing that kind of fits your whole kind of halo, but it looks almost circular. In the sausage plot, it doesn't give you like a sausage. But as you go down in mass, you get just this double-lobed dumbbell thing. And if you increase the distance or the energy from the galaxy, then it kind of separates your double lobes. And if you increase time, it doesn't really mix very much, which is the bottom row. Except in the very early times, you see that the two red sides aren't the same height. Okay, which means that it's still phase mixing. So it looks very anisotropic there. And so we're able to fit this very well with a double Gaussian distribution, which is in blue, to the data, which is in red. And then we go back and we're going to start fitting those double Gaussians to the data that we see. So that's what we do. We go and we fit two double Gaussians to the data. And we tried fitting more and less, and we used a Bayesian argument to justify doing two. And you see that it wants to fit two double lobes, or two double Gaussians. There's going to be one at about plus or minus 230 kilometers per second in the u velocity. And then there's going to be one that is actually at about plus or minus 60. So it's not quite at 0, but it looks almost like a single Gaussian at 0. And what you get is that there's some mixture of the two at very low metallicities. Between minus 2.2 and minus 1.4, it's very dominated by this dumbbell shape. And then as you go higher, especially over -1, you just get this almost single Gaussian shape. And so it looks a lot like you have two things here, because you can't get something that looks like just in the previous simulations. You just get either something that's in the middle or you get something that's not in the middle. You get that double lobe. Well, we get a mixture, which makes it seem like we have something that is, there's one that's in the middle and there's one that is the double lobe structure. And you can actually, because we have this separated out by metallicity, you can just look at the MDF for these structures. And you get that there's that big double lobe velocity structure that peaks at about minus 1.7 or so. And then you get that single one that has a very, not really dwarf galaxy looking MDF, but it peaks at like -1, which is what you saw in Jesse's data. And so you can imagine if you took that blue MDF and you kind of shifted it over to -1, then you would have a little bit of thick disk contamination, and then you would have some junk over on the left at very metal poor that could potentially just be an accretion background of very small minor mergers that were very metal poor. But so the blue is actually consistent with our Virgo radial merger, and the orange is consistent with a Gaia sausage, along with other contaminations. But the key thing here is that actually the Virgo radial merger and the Gaia sausage stars are comparable in the local solar neighborhood. They contribute roughly the same number of stars. And so the conclusion is that this is a cautionary tale, right? You have to be really, really careful about what you're pulling out when you're saying, let's just go for this sausage thing, let's do metallicities, because we believe that if you grab that sausage in velocity space, you're really grabbing two different structures. You're grabbing the thing on the side, which is the Virgo radial merger that actually makes it look like a sausage, and you're grabbing that potentially very old thing that might have fluffed up the thick disk that is in the middle. And so that's it. Thank you.
What are your photometric metallicity errors, and what bands do you use?
Yeah, so they're the bands are the Gaia BPRP. And so then you make a CMD in like Gaia G versus some color that you derive from Gaia color. And the errors are something like 10%. It can go up depending on how bright the star is, but it's not really too bad, especially when you're doing like photometric metallicities. And when you're doing a large number of stars too, and you're just looking at populations. With the large bins that we have in metallicity, it tends to not matter too much.
Thanks for the awesome talk. So one point that I want to ask you about was if you thought about the connection of the Virgo overdensity and the Hercules Aquila cloud. So HAC is another overdensity in the galactic south that we think to be, along with VOD, the two apocentric pileups of stars from the GSE merger. And if you think that GSE actually had an initial metallicity gradient, because it is a dwarf galaxy, or is it a galaxy, then you could have a situation where the two lobes, the two overdensities resulting from the first infall will have a different metallicity peak than the rest of the stars.
Yeah, that's a really good point. So when we fit star to the Virgo overdensity, the orbits actually do go and pass through the Hercules Aquila cloud. So you recover that second overdensity. And interestingly enough, you actually get that the orbits pass through the Hercules Aquila cloud in the north, which is above the disk, which is a large component of that overdensity that isn't actually explained by a big triaxial orientation of the halo. So you can have something that is aligned in a triaxial halo, like what you have, and on top of it, you can have substructure that's aligned with it, because apparently everything, the Magellanic Clouds, are all aligned with it too, that populates the same regions. But in order to get a Hercules Aquila cloud in the north, you need it to not be very mixed, because otherwise you just get this big triaxial thing like what you're seeing.
Just wanted to follow up that, like, we do have a in-house simulation of a radial merger like GSC, and we do get like the two VOD and HEC like things, but we can chat later in the
definitely. Time. No, I'd love to talk with the HEC.
That's great.
It's really cool.
Very nice talk. I should talk to you two afterwards. I have lots of thoughts, but the question I have is related to what are you near the turnoff and what the magnitude of your stars are?
Yeah, so the magnitudes are, I don't remember off the top of my head what the magnitudes are. I think we limit it to be brighter than, I want to say 18th mag, but I'm not positive about that.
So the reason why I asked that question is because I'm going to say what I always say, which is that chemistry is very helpful. You can imagine a situation, right, where if you go to your highest metallicity bin and you look at this structure and you say your prediction is that the middle part is the sausage and the outer lobes are something different. And even if you just look at alpha metallicity, Gaia Enceladus should be relatively large, your lobe should be much smaller based on your metallicity distribution, and so you'd expect a different alpha distribution, which is a prediction that you can test automatically. And in fact, the data might already be in the H3 survey to do this.
Yep. Yeah, for sure.
And
right.
so I would check in with
some
H3.
alpha argument.
Right. So what I would do is plot the sausage in the highest metallicity bin, color code by alpha. You should see alpha pop out differently in the lobes compared to in the center.
Right. Yeah. Yeah. Yep. That's a really good thing to do. And we didn't have access to alpha abundances when we did this, but that's absolutely the next step for it, for sure.
And I also mentioned this mostly because as well, like we could get data for you when in a low resolution spectrograph, we can go to G of 19 and still get alpha abundances.
Right. Yeah. It might have been, I don't know what it was, but
cool.
Yeah.
Good work.
Really fun. Jesse asked my first question. Keith asked my second question. I was banking on Keith asking that question. So I get a third question, or kind of it's exciting connections kind of thing. Right. So I remember you and Heidi talking about this a year or two ago, right? When you were looking at the velocity separations and the little velocity structure in the Virgo overdensity. So it seems to me like there's the chemistry. I love Jess's idea of maybe it's a two-component single galaxy. I love your idea of two. So it does seem like the age and the dynamics, the dynamical aging is going to be key for those shell structures. And I'm wondering, like you're talking about how they fade. I think what we want to do probably, we should form a huge collaboration, and we want to look at very high resolution simulations, because then you don't want to run out of resolution to see the shells, and similarly in the data. So if we have enough data and high enough simulations, I'm hoping the substructure velocity in the shells might help us distinguish between two separate events or the same event. Yeah. That's a thought. What do you think? Because you've done some of these.
I think that is totally the case. It's tricky because you very quickly run into the resolution limits in the data. For your shells, you need very fine resolution in your radial velocities to, and when I say radial velocities, I mean from the center of the galaxy. So it depends on all three of your velocities, and the errors propagate to isolate these shells. And so we actually did that. I kind of glanced over it, but that's something that we looked at, and we were able to find shells and kind of time based on how much they had mixed to say that this has to be a young merger event. But with higher resolution comes more data, and you're going to be able to find more shells. But they mix very, very quickly. So I really don't anticipate being able to find clear shells for an 8 gig-a-year-old structure. I would expect that it would be a mixed distribution.